June 30th, 1894, 10:47, N, London. A bascule weighing 1,200 tons begins to rise. The Countess of Dufferin stands on the south approach. Scissors in hand, ceremonial ribbon already cut. Behind her, the crowd holds its breath. Before her, two massive steel leaves tilt skyward, splitting the Thames in half. Somewhere beneath the Gothic towers, in chambers the public will never see, pressurized water screams through iron pipes at 750 pounds per square inch. The engineers watch from the engine houses. Their hands are steady, but their hearts are not. 8 years of construction, 11 million bricks, 5 contractors, 250 workers. All of it rests on a hydraulic system that has no precedent, no backup plan from history, no proven track record. Just mathematics, steam, and faith in redundancy. The bridge opens in 80 seconds. Perfect synchronization. The leaves lock vertical at precisely the same moment. Their 143-foot peaks framing the sky. What the crowd doesn't know, every single component in that hydraulic system exists twice. 2 steam engines, 2 accumulators, 2 sets of pumps, 2 complete hydraulic circuits. The engineers built Tower Bridge with a simple philosophy. If one fails, the other takes over. No delays, no disasters, no excuses. That system would run for 82 years without a single hydraulic failure. This is the story of the machinery they built in duplicate, the pressure they sustained in absolute, and the engineering philosophy that refused to gamble with London's River Dot. The problem begins decades before the Bridge. 1870 S. London. The city spreads east. Docks multiply. Ships grow larger. The Thames becomes a highway of commerce, carrying 25,000 vessels annually through the Pool of London. But the river also becomes a barrier. Tower Bridge doesn't exist yet. The closest crossing is London Bridge, a mile upstream. For the people living and working in the East End, crossing the Thames means walking that mile, crossing, and walking back. Hours of their day vanish into this detour. The Metropolitan Board of Works receives complaints, petitions, demands, build a bridge, connect the city. But here's the constraint. Any bridge must allow tall ships to pass. The Thames is a working river. You cannot block maritime traffic. You cannot lower the masts. You cannot demand that the world's shipping industry redesign their vessels for London's convenience. The solution seems obvious. Build a high bridge. But the approaches would need to rise gradually for horses and carts to climb them. Run the calculations. To reach a clearance height of 135 feet above high water, the approach ramps would stretch nearly half a mile on each side. The solution would consume too much land, too many buildings, too much of the city itself. 50 designs are submitted. Most are rejected within weeks. A few linger. There's a proposal for a subway tunnel beneath the river reserved for pedestrians. Another suggests a high-level footbridge with hydraulic lifts to carry people up and down. The board hesitates. The public debates. The engineers calculate. Then, in 1884, a committee selects the design from Horace Jones, the city architect. His solution, a bascule bridge. 2 massive counterweighted leaves that can swing upward, creating a 200-foot gap for ships. When lowered, they form a continuous roadway. When raised, they clear the river entirely. The design includes high-level walkways for pedestrians to cross, even when the bridge is open, though these will prove unpopular and eventually close. Jones dies in 1887 before construction finishes. John Wolfe Barry takes over as engineer. George Stephenson becomes the resident engineer for the mechanical systems. The real challenge now begins. How do you move 1,200 tons of steel smoothly, quickly, and reliably? Gravity cannot do this alone. Counterweights help, balanced inside the massive piers, but they only offset the load. You need controlled power. You need something that can deliver immense force with precise modulation. You need hydraulics. The decision to use hydraulic power is not romantic. It's practical. Hydraulics in the 1880s are proven technology. Docks use hydraulic cranes. Factories use hydraulic presses. Ships use hydraulic steering. The principle is simple. Pressurized liquid transmits force. Compress water in one chamber, and it pushes a piston in another. The advantage: hydraulics can deliver massive force smoothly, without the jerking violence of gears and chains. The disadvantage: if the system fails, the bridge cannot open. Stevenson and his team designed the hydraulic system with one non-negotiable requirement: total redundancy. They will duplicate everything. Not for efficiency, not for speed, for reliability. If one component fails, the bridge must still function. London cannot afford a broken bridge. Blocking its river. The system begins with steam. 2 coal-fired steam engines, each producing 360 horsepower, drive the hydraulic pumps. These are not small machines. Each engine weighs over 50 tons, with cylinders measuring 18 inches in diameter and pistons driving a 4-foot stroke. The engines sit in the South Engine House, a Gothic Revival building that matches the bridge's ornate towers but serves purely functional needs. The steam engines don't operate continuously. They work on demand, activated when bridge operators anticipate a ship requiring passage. Their job: pump water from the Thames, filter it, and force it into the accumulators under pressure. The accumulators are the heart of the system. Think of them as hydraulic batteries, storing pressurized water for instant use. Each accumulator is a massive vertical cylinder containing a weighted ram. Water pumped beneath the ram forces it upward, compressing the stored energy. When the bridge needs to open, valves release this pressurized water into the operating cylinders. The accumulators maintain pressure at 750 pounds per square inch. Constant, reliable, ready. Tower. Bridge has 2 accumulators. Each stands 47 feet tall, weighs 125 tons, and can store 60 tons of water under full pressure. Together, they hold enough energy to open and close the bridge multiple times without running the steam engines. This isn't just redundancy. This is resilience. The system can handle sudden demands without lag time, without waiting for steam pressure to build. From the accumulators, the pressurized water flows through a network of pipes to the operating machinery beneath each bascule leaf. Here, the water enters hydraulic cylinders. These are not ordinary cylinders. Each one measures 18 inches in diameter with a 9-foot stroke. Each bascule has multiple cylinders working in concert. When pressurized water enters, the pistons extend, pushing against massive cranks connected to the bridge leaf. The mechanics are hidden beneath the roadway, inside the stone piers, invisible to anyone crossing above. But here's where the redundancy becomes explicit. The hydraulic circuits are completely separate. One circuit can operate the entire bridge independently. If a pipe bursts in Circuit 1, Circuit 2 takes over. If an accumulator fails, the other maintains pressure. If a steam engine stops, the second engine continues. The bridge operators can switch between systems with a series of valves, rerouting pressure instantly. The control room sits in the North Tower. 4 men work each shift. They monitor pressure gauges, listen for warning bells, and watch the river. When a ship approaches, signals are sent. Red balls rise on poles to warn road traffic. Bells ring. Gates close. Then, with the turn of a wheel, the hydraulic valves open. The bridge rises. Opening day proves the system. The Countess performs her ceremony. Dignitaries make speeches. Journalists document every detail. But the engineers watch the gauges. 75 psi. holding steady. The first ship passes through. A steamship, mid-sized, nothing dramatic. The bascules rise in 1 minute and 12 seconds. They hold vertical for the ship's passage. They lower in 80 seconds, perfectly synchronized. The hydraulic system consumes approximately 20 tons of water per opening cycle, drawn from the accumulators and then replenished by the steam pumps. The public marvels at the Gothic towers, the blue paint, the Victorian splendor. The engineers marvel at the machinery. No leaks, no pressure drops, no hesitation. The system works exactly as designed, but working on opening day is not the same as working every day. The real test begins now. Tower Bridge opens an average of 20 times per day in its early years. Some days more. The Thames is busy. Ships arrive on unpredictable schedules. The bridge must respond immediately. Wait too long, and traffic backs up on the river. Rush the operation, and you risk mechanical failure. The hydraulic system settles into routine. Steam engines fire up in the morning. Pumps fill the accumulators. Pressure stabilizes at 750 psi. The system idles, ready. When needed, valves open, water flows, pistons extend, the bridge rises. When the ship passes, reverse valves engage. Pressurized water flows to the opposite side of the pistons. The bascules lower. Gravity and hydraulics working together, controlled descent, no slamming, no shock. Each opening cycle generates heat. Pressurizing water, forcing it through pipes. Extending pistons under load friction converts energy into temperature. The hydraulic system includes radiators and cooling systems to dissipate this heat. Without cooling, the fluid would overheat. Viscosity would change, seals would fail. The engineers plan for this. They install heat exchangers that route cooling water from the Thames through the system. Carrying away excess temperature. Maintenance becomes ritual. Every week, engineers inspect the pipes, checking for corrosion, wear, and vibration damage. Every month, they drain and inspect the accumulators, examining the seals and rams. Every quarter, they disassemble the hydraulic cylinders, replacing worn components before they fail. This is preventive maintenance, a concept still novel in the 1890s. Most industries run equipment until it breaks, then fix it. Tower Bridge cannot afford that approach. The redundancy proves its value repeatedly. In 1897, a valve packing fails in one of the steam engines. The engine loses pressure. The bridge operators don't panic. They switch to the second engine. The bridge continues operating. Repairs happen during low traffic hours. No delays. No emergencies. In 1902, a hydraulic pipe develops a hairline crack in one circuit. The pressure gauge shows a slight drop. Again, operators switch to the backup circuit. The damaged pipe is isolated, replaced, tested, and returned to service. Total downtime. 0. This is what redundancy buys. Time. Time to diagnose. Time to repair. Time to solve problems without crisis. The system evolves, but carefully. In 1910, the engineers install improved pressure gauges with finer calibration. The original gauges work, but better measurement means better control. The new instruments allow operators to detect pressure variations of less than 5 psi, providing early warning of developing issues. In 1924, they upgrade the steam engine's boilers, improving thermal efficiency. The old boilers consume coal at a rate that becomes increasingly expensive as fuel prices rise. Post-World War I, the new boilers extract more steam from less coal, reducing operating costs without changing the core hydraulic system. But the fundamental architecture remains unchanged. 750 PSI, 2 of everything. Hydraulic power. This isn't conservatism. This is recognition that the system works. Why introduce risk by redesigning something that has proven reliable? The operational records tell the story. From 1894 to 1976 to 82 years. The hydraulic system opens and closes. Tower Bridge, approximately 6,000 times per year on average. Some years more, some less, depending on maritime traffic patterns. That's nearly 500,000 operating cycles. 500,000 moments where 2,400 tons of steel must move smoothly, stop precisely, and lock securely. The hydraulic system never fails catastrophically. Never leaves the bridge stuck open. Never drops a bascule. Never loses pressure entirely. There are minor issues. Seals that wear, pipes that need replacement, valves that require adjustment. But the redundancy absorbs these problems. The bridge keeps functioning. Engineers from other projects visit Tower Bridge to study the system. They take notes. They ask questions. How do you maintain pressure so consistently? How do you prevent water contamination? How do you balance the load between circuits? The answers are not glamorous. Regular inspection, quality components, proper training, redundant design. Do the basics well every time, and the extraordinary becomes reliable. The world changes around Tower Bridge, but the hydraulic system persists. World War I brings different challenges. Maritime traffic shifts. Naval vessels pass through. The bridge opens for warships, for supply convoys, for hospital ships returning wounded from the continent. The hydraulic system works through it all, indifferent to the cargo it facilitates. World War II intensifies the demands. The Blitz targets London. Bombs fall on the Thames. Tower Bridge survives, though nearby buildings collapse into rubble. The engine houses take minor damage from blast concussion, but the hydraulic machinery endures. Engineers work through air raids, maintaining the system, ensuring the bridge can still open if needed. It's not heroism. It's duty. London needs the bridge. The bridge needs the hydraulics. The hydraulics need maintenance. Post-war, shipping patterns shift again. Container ships emerge, larger than Victorian-era vessels. Oil tankers grow massive. But Tower Bridge, with its 135-foot clearance when open, accommodates them. The hydraulic system doesn't care about the ship's size. It cares about pressure, timing, and synchronization. These remain constant. By the 1950s, diesel engines begin replacing steam in many industrial applications. Tower Bridge resists this trend initially. The steam engines work. They're familiar. The engineers know every quirk, every sound, every maintenance requirement. Changing power sources means retraining operators, redesigning systems, accepting new failure modes. But economics eventually force the issue. Coal becomes expensive. Steam engine maintenance becomes costly. Boiler regulations tighten. In 1974, the decision is made. Convert to electric hydraulic operation. This is not a simple swap. The entire power system must be redesigned. Electric motors will replace steam engines. Modern hydraulic pumps will replace the Victorian-era originals. But the core principle remains: maintain pressure, preserve redundancy, keep two independent circuits. The conversion takes 2 years. Engineers work carefully, replacing components section by section, testing each modification before proceeding. They cannot shut down Tower Bridge entirely. The river still needs passage. The road still needs crossing. The conversion happens incrementally, one circuit at a time, with the backup system always ready. On October 1st, 1976, the steam engines shut down for the final time. They've run for 82 years. The electric motors take over. The hydraulic pressure remains 750 psi. The bridge opens and closes just as before. From the road above, nothing has changed. From the control room, everything has changed. The Victorian hydraulic system is retired, but not destroyed. The steam engines, accumulators, and pumps are preserved. The engine houses become museum spaces. Visitors can see the machinery that moved Tower Bridge for 8 decades. They can stand beside the massive accumulators, touch the iron pipes, examine the steam cylinders. The equipment sits silent now, but complete, a monument to redundant design and sustained reliability. What made the system work? Not innovation alone. The hydraulic principles were established technology. Not size alone. Larger hydraulic systems existed in docks and factories. Not redundancy alone. Duplicate systems are pointless if both are poorly designed. The success came from integration, proven principles, massive scale, total redundancy, and relentless maintenance. The engineers built a system where failure was difficult because failure required multiple simultaneous breakdowns in independent circuits. They maintained that system with discipline that never wavered. They operated it with procedures that minimized human error. Consider the pressure, 750 PSI. This is not arbitrary. It's the sweet spot between force and safety. Higher pressure delivers more power per unit volume, allowing smaller cylinders and lighter components. But higher pressure also stresses pipes, seals, and fittings more severely. Exceed material limits and failures accelerate. 750 PSI pushes the boundaries of Victorian-era materials without breaking them. It's aggressive engineering tempered by respect for physics. Consider the redundancy philosophy. They didn't build 90% backup. They built 100% duplicate. Either circuit alone could operate the bridge fully. This is expensive. It doubles material costs, doubles installation complexity, doubles maintenance requirements. But it eliminates single points of failure. If you're building a bridge that cannot fail without blocking London's primary river, doubling your costs is not extravagance. It's necessity. Consider the maintenance culture. Victorian engineers understood something often forgotten in later decades. Machines don't fail randomly. They fail predictably, after measurable wear, following observable patterns. Inspect regularly, measure carefully, replace components before they break, and you transform reliability from hope into science. Tower Bridge's engineers didn't wait for failures. They hunted for problems, found them early, fixed them while the backup system covered. The result: 82 years without hydraulic system failure. Not 82 years without problems. 82 years without failures that mattered, without breakdowns that stopped the bridge, without disasters that blocked the river. Tower Bridge today operates on oil hydraulic systems, more compact and efficient than the original water-based machinery. Electric motors provide power. Computer controls manage timing. But the principle remains. When ships approach, the bridge opens. The opening takes approximately 90 seconds now, slightly faster than the Victorian system's timings. The mechanisms are hidden. The process is smooth. And the tourists taking photographs rarely think about the pressure, pistons, and engineering beneath their feet. The original hydraulic system sits preserved in the engine houses, accessible to visitors who descend from the high-level walkways into the chambers where the machinery lived. You can stand in front of the accumulators, massive cylinders that once held 60 tons of water at 750 psi. You can see the steam engines, their flywheels motionless, their pistons frozen mid-stroke. You can trace the pipe runs, follow the circuits, identify the redundant pathways. The interpretation is imperfect. Plaques explain the basics, but they cannot convey the sound of steam engines driving pumps at full power, the hiss of pressure valves opening, the groan of pistons extending under load. They cannot capture the tension in the control room when both circuits showed pressure fluctuations simultaneously, or the relief when the problem turned out to be a faulty gauge, not actual pressure loss. They cannot replicate the discipline of engineers who maintained the system through 2 world wars, economic depressions, technological revolutions, and 82 years of daily demands. But the machinery speaks anyway. Its silence is articulate. It says, "This worked." For nearly a century, this exact equipment moved one of the world's most iconic bridges without catastrophic failure. The engineering was sound. The redundancy was necessary. The maintenance was sufficient. The 750 PSI system that Victorian engineers calculated, built, and trusted proved worthy of that trust. Why does this matter now? Because engineering is often about the invisible. The bridge above its Gothic towers, blue paint, and architectural drama, it's photographed millions of times per year. It's iconic, recognizable, beloved. But the machinery below did the real work. It moved weight. It created clearance. It made the bridge functional, rather than decorative. Modern engineering often forgets redundancy. We optimize for efficiency, minimize redundancy as wasteful, trust that single systems will suffice if designed well enough. Sometimes this works. Sometimes it fails spectacularly. A single O-ring destroys a space shuttle. A single sensor error crashes an airplane. A single circuit failure blacks out a city. Tower Bridge's engineers assumed failure. They planned for it. They built 2 of everything not because they expected daily breakdowns, but because they knew eventual breakdown was certain. Something, somewhere, would fail. The question was not if, but when, and what would happen next. By building complete redundancy, they transformed, when something fails, from disaster into inconvenience. A valve packing fails? Switch to the backup circuit. A pipe cracks? Isolate and repair while the other circuit operates. A steam engine loses pressure? The second engine continues. Failure became manageable because the system was designed to fail gracefully. This is the lesson. Not that redundancy prevents failure, but that it transforms failure's consequences. The 750 PSI system succeeded not because it never had problems, but because its problems never mattered enough to stop the bridge. The final statistic: 500,000 operating cycles without hydraulic failure. That's the number that matters. Not the weight of steel, not the volume of water, not the Gothic architecture or the blue paint. 500,000 times, the hydraulic system did exactly what it was designed to do. It moved massive counterweighted bascules smoothly, stopped them precisely, held them securely, and lowered them safely. The engineers who built this system are long dead. The steam engines are silent. The accumulators are depressurized. But the bridge still opens, still clears the river, still connects London across the Thames. And somewhere in the archive of engineering history, there's a lesson written in pressurized water and duplicate circuits. When you cannot afford failure, build for redundancy. When you expect decades of service, build for maintenance. When you're moving 1,200 tons repeatedly, build with precision. The 750 PSI system that never failed in 82 years wasn't magic. It was mathematics, materials, and relentless attention to detail. It was Victorian engineers who understood that the spectacular parts of the bridge would capture attention, but the hidden machinery would determine whether the bridge actually worked. They built it with 2 of everything. They maintained it with discipline. They operated it with skill. It worked. For 82 years, it worked. That's engineering.